Hello everyone and welcome you back for the physics class. For today's class I will be discussing with you the topic energy of an electron. We are discussing the chapter atoms, and then under that particular chapter we have already covered the Rutherford's atom model, where we have discussed the alpha scattering experiment, as well as we discussed the the postulates or the conclusions of the Bohr's experiment. After that, what is his drawbacks, and after that we have started our Bohr's model, and in that model we studied postulates as well as we have derived the Bohr's radius. So for today's class, our main aim or the objective is to know the energy of an electron. Then after knowing the energy of an electron, we will be discussing the spectral lines in an hydrogen atom. It's okay. So let's start the class, begin the class with the topic energy of an electron. So topic is energy of an electron. So when I say energy of an electron, it means that the electron is revolving around the nucleus. So what will happen? It will have energy. So it will possess some energy. So what are the types of energy it might have? Basically, when I am saying it is moving, so it will have mechanical energy. As it has mechanical energy, so I can say that it will have kinetic energy as well as a potential energy. So the two types of energy that is associated with the electron while revolving around the nucleus is number one, kinetic energy. Got it? So if I say kinetic energy, I hope you remember the formula for kinetic energy. The kinetic energy is given by half of mv square. So I will write here Ek is equals to half of mv square. It's okay. Now here mass m is the mass of the electron and v is the velocity of the electron. And after that, while deriving the radius of the Bohr orbit, I hope you remember we have studied that whenever an electron, this is the nucleus Zi, and an electron is revolving around it, what will happen? This is also positive charge, this is a negative charge. We will get an electrostatic force of attraction. And as it is moving in a circular path, so it will have centripetal force, and from there we say that the necessary centripetal force will be provided by the electrostatic force of attraction between the nucleus and the electron. So if I use that particular concept, so we can write, we know mv square, this is what? By r, this is the centripetal force. It comes from whom? It comes from the force of attraction between the charges, between a nucleus. So I can write K, Ze is the charge of the nucleus and E is the charge of the electron. So I can write Ze square divided by r square if I consider r to be the radius. So from here I can write mv square is equals to K Ze square divided by r. So this is my mv square. Now substitute this equation here, then what I will get? Kinetic energy is equals to half of, means kZe square divided by r. So this is the kinetic energy associated with an electron which is revolving around the nucleus. So we came to know about kinetic energy. So I will keep this equation somewhere. I will write, let me keep this equation. So I have a place here. So I am writing, I have already derived Ek is equals to half of kZe square divided by r. So this is my formula first that I have written. I have not derived anything, I have just written. What is the second form of energy associated with an electron? It is the potential energy. It's okay, so it is the potential energy. Now we have to calculate this potential energy. So potential energy, here charges are there. So if charge is there, obviously it will come from electrostatics. So if it is electrostatics, there we have studied potential energy of a charge. I hope you remember. Actually potential energy is nothing but it is the work done. And there we have written potential energy U is equals to half, we have written K Q1 Q2 divided by r square. This equation comes from the second chapter of the first book, that is electrostatic potential and capacitances. There we have derived it also, we have used it also. So I hope you will not find any difficulty. Now in our case here K will remain the same, but what will happen to E, Q1? See, one is the nuclear charge, another one is the charge of an electron. So if I consider Q1 to be charge of nucleus, I will write QE, ZE, sorry. And if I consider Q2 to be the charge of the electron, I will write E. Isn't it? Yes, E. But my one question here. Energy is a vector quantity or a scalar quantity? It's a scalar quantity. Since it is a scalar quantity, so I have to write, if it is negative, I have to write with negative. We have done the numerical in the same way in that particular chapter. So divided by R. So I will get this equation as minus K ZE squared divided by R. So what is the potential energy associated with the electron? This is the potential energy associated with the electron. So I will write this here. So it will be minus KZE squared divided by R. So if I get the kinetic energy, if I get the potential energy, can I tell the total energy of the electron? So what will be the total energy of the electron? The total energy of the electron, if I write this as E, it will be equals to sum of the kinetic energy and the potential. I know this is, so if I solve this at this, I will get the formula minus half of KZE squared divided by R. So the total energy is equals to this. So I can write here E is equals to minus half of KZE square divided by R. Now if I compare these three equations, I can say that E is equals to negative of kinetic energy. I can say, I think, yes, we can see. Similarly, if I write total energy E is equals to, again negative is there. If I want to write in potential term, then I have to write what? Twice of potential energy. Will it be okay? Or half of? So, how can we do it? If I use this one, this part is entirely what? This. Sorry, now this is half, this will be, get U by 2, not half. So we have a relation with this, means with kinetic energy and potential energy. Please remember this, so that you can use it in your some questions where only kinetic energy, potential energy is given. Then you have to find a total energy. That concept you have to use it here. But some students, they don't do like that. If it is total energy is given, they will put in the formula. They will try to find out R. No need to do all these things in that particular case. Okay. So if we got this relation, but what is my R? R is my m square h square divided by 4 pi square m k z square e to the power 4, I think. It is e to the power 4 or e square? Sorry, it is z e square. Sorry, it's a z e square. So this is my formula for R. If this is the formula for R, so if this is the formula mk square, okay, so if I substitute this value here, what will be my total energy? E will be equals to minus, then half will remain the same, k z e square by z square, I will take common. Then I can write here 4 pi square m k z e square divided by m square h square. So if I solve it, I will write minus twice of pi square, done, m k square z square e to the power 4 divided by m square h square. So this is my total energy in terms of n. So we got the total energy in terms of n as 2 pi square m k square z square e to the power 4. So this is the total energy associated with an electron. Now, as I came to know about the energy of an electron, so because of this energy of an electron, there will be some spectral lines. So let's move to the topic, spectral lines. So I will write this formula that I have already derived. It is minus 2 pi square m k square z square e to the power 4 divided by m square h square. So whatever we have done, I have written there by the side of the board. So next we will be discussing spectral lines of hydrogen atom. So spectral lines of hydrogen atom. Suppose I say that we have an n orbit, and we are writing the energy for a hydrogen atom. Okay. Now see, you might be confused that hydrogen atom has only one shell. One means orbit. But taking into account that hydrogen atom, if it is hydrogen atom also, that one will not be a one level. Means suppose whatever we have studied, this is the nucleus, this is my first orbit, this is my second orbit. Actually this is K shell, this is KL shell. It's like that. But what happens, we get energy bands here. Band will be there. It is not a one level. It will have lots of together. So many levels will be there. So for that reason, when I am writing 1, 2, 3, 4, it doesn't mean K, L, K, J, K, L, maybe. So here N will be different. But K for hydrogen atom, sorry, Z for hydrogen atom will be 1 because it is only one proton and one electron. So if I say for nth orbit, in case of a hydrogen atom, so En, if I will write, it will be equals to minus 2 pi square mk square e to the power 4 divided by n square h square. So this is my total energy in the nth orbit of a hydrogen atom. Now, by suppose I say this is a energy level En2 I have written. This is another energy level En1 I have written. And I say that En2 is greater than En1 and the electron is in the higher energy level. Already I taught you in the Bohr's frequency condition that if an electron is in the higher energy state, what will happen? It will jump to the lower energy state with the release of photon of energy h. It's okay? So this concept we have studied from which law? Which postulate? Bohr's third postulate, which is the Bohr's frequency condition. After that, if I ask you write down this level is N2, this level is N1. Suppose I ask you to write down the energy for En2. We can write En2 is equals to same thing minus 2 pi square m k square e to the power 4 divided by N2 square h square. Similarly, En1 will be equals to minus 2 pi square mk square e to the power 4 divided by N1 square h square. So this is my formula for the one level, this is the formula for the other level. So according to Bohr's frequency condition, what happens if the electron jumps to the lower energy level, it will emit an photon of energy h nu. Then I can write here by Bohr's frequency condition. I am writing the entire sentence and condition. What I can write, En2 minus En1 is equal to h. I will do shortcut now. Please don't mind because I know you can do it easily. So what I am going to do, left hand side I will write h nu, right hand side now see. En2 my this value and En1 my this value. Here everything is same except N1 and N2. So I can take 2 pi square mk square e to the power 4 divided by h square as common. My first term is En2, so minus of En2 square. Then again minus will be there, but minus here also minus, so minus minus plus will be there. So N1 square bracket close. So from here I can write h will go down, so nu will be equals to 2 pi square m. This is just a calculation, means we are just changing here and there. Now see, this is minus, so can I write 1 by N1 square minus 1 by N2 square? So I have written like this. What is frequency? We have studied in class 9 also as well as in 11 also that velocity equals to velocity. Another formula, velocity is equals to nu into lambda. Since we are talking about electron revolving and all, so this c velocity will be speed of light, which is nu into lambda. So I can write from here c by nu is equals to lambda. Okay. So nu is there. So if it is nu, then I can write C by lambda is equals to 2 pi square m k square e to the power 4 divided by h cube into 1 by n1 square minus 1 by n2 square. This formula I wrote. Huh? Now after writing this formula, if I ask you, can I write this as a 1 by lambda is equals to 2 pi square m k square e to the power 4 divided by c h cube. The entire term, middle term will remain the same. Now this is entirely a constant term. This is my c. Don't get confused. This is my e. This is entirely a constant which is known as the Rydberg constant. Rydberg constant. And the other term will be 1 by n1 square minus 1 by n2 square. And this is equals to nu bar, I will say. What is nu bar? Nu bar is the wave number. And what is my r? R is my Rydberg constant. It's okay. So this is my derivation for today's class. So with the help of this, we will do some numericals in the next class, and along with that, we will discuss some other factors also. Okay then, till then, thank you all. Have a good day.